In this video, we'll be introducing the idea of parametric equations, and in doing so, introducing one of the common themes throughout this course, which is using different methods to represent the same thing, whether we're talking about curves or surfaces or what have you. If we have these different options for ways to represent objects, then we can choose whichever one ends up being most convenient or easiest to work with, depending on what we're trying to do. Some of these representations may be easier to differentiate or integrate than others, and so we want to have all of them at our disposal in order to make our lives as easy as possible. The first one here with parametric equations, the idea is that we have x and y, our variables, and we consider them continuous functions of some other variable, in this case a parameter t. If x and y are continuous functions of t on an interval I, then the equations x equals x of t and y equals y of t are called parametric equations with that parameter t. Note here in each of these equations we have two different uses of both x and y. The x and y that are on their own are the variables that we're thinking of when we're considering the points in the plane, whereas the x and y with x of t and y of t, these are function names. If we have these parametric equations, then the set of points x, y, these are the ones on the left side of the equation now, those points that are obtained as we let t vary over the interval I, this gives us the graph of the parametric equation. And we call that graph a parametric curve, denoted by a capital C. Since this curve does reside in the xy plane, we also refer to it as a plane curve, as we will with any other curve that exists in a specific plane rather than being out in three-dimensional space. The first thing we're going to want to do with these parametric curves is figure out how to graph them. And there are two main methods that we can use to do so. The first one is point plotting, and this is going to work out very similarly to the point plotting method that we would use for rectangular curves in x and y. In the rectangular curves, we would let x be our independent variable and choose different values of it and plug into the equation in order to figure out y. It's similar here, except there's more stuff for us to plug into. In this case, we choose values of t in our interval, usually equally spaced, but they don't necessarily have to be. But we choose values of t on our interval I, and evaluate both x of t and y of t for each one. That's going to result in a series of points, x of t, y of t, which we can then plot. One thing that makes this a little bit different from just plotting a regular rectangular curve is that the parameter t has a naturally increasing value over the interval I. So what we can think of here is we can imagine moving along the curve from the small values of t to the large values of t. This gives each of our parametric curves kind of an inherent direction, and we call that direction the orientation of the curve, which we indicate by drawing little arrowheads along the curve. Now this point plotting method again is kind of like a brute force approach, which makes it always viable for graphing our parametric curves, but it can be time consuming because you have a lot of stuff that you're plugging into. Especially if you have a large interval and a complex curve, you may need to plot a whole bunch of points before you really get a sense of what your curve is looking like. That being said, we do have an alternative that can be easier, but it does require a little bit more prior knowledge on our part. And that method is eliminating the parameter. The goal here is to rewrite both of those parametric equations as a single rectangular equation in x and y. If we have that single rectangular equation in x and y, we can use what we know about functions that we've seen in the past, and based on that equation say, okay, what type of curve is this going to be? Where is it going to be located? What properties do we know about this curve? The way that we eliminate the parameter is as follows. First, solve one of the equations for the parameter. It doesn't really matter which one. I would recommend solving whichever one is simpler, but largely up to you. Once you've done that, substitute that expression into the other equation in place of the parameter. This is going to eliminate the parameter entirely, and you're just going to have an equation in x and y. Once you've done that, then solve for one of the two variables and identify the curve. Now there are some cases where you don't actually need to solve for one of the two variables in order to identify the curve. Things like ellipses, things like circles. If you have those sorts of equations, you don't really need to solve for either one in order to recognize the equation, but most of the time you will want to pick one of the two variables and solve. Once you've done that, once you know what the curve is going to look like, we then need to find the starting and ending points for the curve using the given interval. Because the equation that we get in x and y is not going to have the inherent restrictions on the parameter that we would have in the parametric equation. So we want to make sure that we see where this curve is starting and where this curve is ending to make sure that we don't go beyond that. In doing so, we are also inherently finding the orientation of the curve as well. So we're kind of implementing all of that stuff for the parametric side of things into this rectangular curve by keeping these things in mind. And as I mentioned before, this can be quicker than point plotting, but it does rely on prior knowledge of the equations that different curves have. If you are not familiar with a lot of the equations for different types of curves, then this may not be ideal for graphing your parametric curves. And sometimes it can require a little bit of creative problem solving if you have parametric equations that aren't so easy to solve for the parameter. But again, if you can do that, then this oftentimes ends up being a little bit quicker. In addition, with our parametric equations, we can go in the opposite direction. Take a rectangular curve and come up with parametric equations to represent it. This is a method called parameterizing the curve. We are essentially defining our set of parametric equations to describe the curve that we already know we have. One thing to note here is that any given plane curve can be parameterized a number of different ways. These parameterizations are not unique. The way we do this is by defining a parameterization for our independent variable and then replacing that into the equation in order to find the other parametric equation. So as you can see here, the simplest one involves just saying x of t is t, and then replace the x in the curve's equation with the parameter t, and you get your other equation y of t. That will result in the same set of points x, y as x of t and y of t. But you don't have to. You can use any other parameterization that you want. You can set x of t to be literally anything that you want, and then whatever you choose there, plug that in for x in the curve's equation, and simplify as much as you can, and you'll get your other equation y of t. However, we must be a little bit careful here to identify any restrictions on the domain of the parameter t if they exist. So if there are any points or any values of the independent variable x that don't exist for your original curve, then you need to make sure that that's reflected in the parametric equations as well. And that's where things can sometimes get a little bit tricky. Of course, this is all well and good if we can switch back and forth between rectangular and parametric equations for curves that we know, but there are some examples of parametric curves that you can represent fairly easily with parametric equations, but are very, very difficult to manage using rectangular equations. One example of this is a cycloid. A cycloid describes the path that's traveled by a point on a circle as that circle rolls along a straight line. We can do that with the equations x of t equals a times t minus sine of t, where a is the radius of the circle, and y of t equals a times 1 minus the cosine of t. And if we take a look at this animation here, this is showing the path for the cycloid. At the end of the radius on the circle is the point that we're interested in, and the animation is tracing out the path of this cycloid as the circle rolls along that straight line, in this case the x-axis. So we're tracing out this path where it looks kind of like it's going along a circular arc, although it's not actually a circular arc here. But then when it gets back down to that height of 0, then it starts going up again. This sort of curve would actually be really difficult to represent as a rectangular equation, but we have these relatively simple parametric curves that we can use to represent this cycloid. Another example that would be even more difficult to represent rectangularly is a hypocycloid. And this is similar to the cycloid in the sense that we're following the path traveled by a point on a circle. But now, rather than traveling along a straight line, that circle is rolling along the inside of some larger circle. And this can result in a wide variety of different looking curves, depending on the ratio of the larger circle's radius to the smaller circle's radius. And that's reflected in these equations as well. For a hypocycloid, if you have the large circle's radius being a and the small circle's radius being b, you have the equations x of t equals a minus b times cosine t plus b times the cosine of a minus b over b times t. And then y of t is basically the same thing, just with signs in there and switching the operation. Now again, these hypocycloids, their form is going to depend upon the ratio of these radii. So if we have this outer circle here and this particular inner circle, and we start animating this, let's move the speed up a little bit so it goes a little faster. The path that that point on the inside of the circle, or on the edge of the inner circle, travels, that's going to be the curve for our hypocycloid. Now if I change the radius of this inner circle here, let's say I make this 80 pixels instead, I'm going to get a completely different graph. Now you can imagine this is going to be very difficult to reflect in a rectangular curve. Right? It's definitely not a function rectangularly. Right? This would fail the vertical line test pretty miserably. But using those parametric equations that we had in the slides, then as long as we know the values of a and b, these can be used to represent that curve in all of the different sorts of forms that this curve can take.